Good morning, everyone. Today we're looking at stoichiometry. Now, stoichiometry is when you've got one substance and there's an equation, and then they ask you another substance in that equation. And here you're always going to work with ratios. When the substance that they give you is not the substance that they ask, then you must use the ratio, right? And even if it's 1-to-1, you have to show it's 1-to-1. So let's look at the first example there. I ask you to calculate the mass of sodium oxide. So this is what you're looking for. And I find a nice way to keep book of this is to go and write down the equation and then write down what they give you and what you need. And this time, mass is my unknown. So this is where I want to end up. I want to work out the mass of that sodium oxide. And remember, you will have to go through moles first. So first you'll work out the moles and then you will calculate the mass. Now I like to write moles just underneath that equation because that equation is giving you the ratio in which things are going to react. This is telling you 4 moles of the sodium will react with 1 mole. If there's nothing, there's obviously a 1 mole of oxygen, and that will give you 2 moles of sodium oxide. So just underneath, I'm writing down N, that is my moles, and then underneath that, I'm going to write what they give me and what I need to find. Now here they ask us to calculate that mass that can be produced when 4,93 cubic decimeters of oxygen gas at standard temperature reacts with an excess of sodium. So I know I've got a volume there of the oxygen of 4,93. They're very nice to us. They give us standard temperature and pressure. So it will be easy to convert that to moles. And then you need to go from moles of oxygen to moles of sodium oxide. So first we start with the volume of that oxygen and we convert the volume of the oxygen to moles. Now we've done that a lot. You are very good with that. We've worked out the moles of oxygen and now we want to move over to the moles of sodium oxide. Now we're going to say O2 to Na2 is always in the ratio 1-to-2. So 1 mole of oxygen will give you 2 moles of sodium oxide. But I don't have 1. Remember, I've worked out 0,22. So now I want to know how many moles of sodium oxide will that produce. So this, if it's easy like this, you can just multiply by 2 because they're in the ratio 1-to-2. But if the maths was difficult, then I would have said 2 times 0,22 is going to be the same as 1 times x, doing a cross multiplication, and then just solving for x. Now I've worked out how many moles of sodium oxide I've got, and now it's just plain conversion to mass. Now remember, if the moles they give you is for sodium oxide, then the molar mass down there must also be for sodium oxide. And be very careful, that 2 does not come in to the mass, right? It's not part of that molar mass. That 2 is only used in that ratio. So the 2 is already used. Don't use the 2 with the molar mass. The molar mass is just for that substance, sodium oxide, and that's where you get 62. It's 23 for every sodium, and there's 2 sodiums, and then 1 oxygen with 16, and that's how you end up with 62. Let's do one more example, and then you are going to practice this. In our first example, they ask you what mass of butane, you don't need to know it's butane, C4H10, is required to react completely with 4,48 cubic decimeters of oxygen gas at standard temperature and pressure, and they give you this equation. So first let's think what we have to do. They are giving you the volume of the oxygen gas and they're asking you for mass. So what I need to do is I need to convert that volume to moles, and that will be moles of oxygen, and then the stoichiometry going from oxygen to butane. And once I have that moles of butane, then easy conversion to mass. So this is an easy one. Starting off with the volume, and we are at standard temperature and pressure, that's going to be easy. If we are at standard temperature and pressure, I'm using 22.4, and I get my moles of oxygen. Now I've moved up to there. Next up, stoichiometry, going from oxygen to butane. So I'm going to start with that ratio. Butane to oxygen, according to my equation, it's in the ratio 2 to 13. 2 to 13. And then I'm going to say, but I don't have to. I have 0,2. So here you can do cross multiplication, or you can just divide by 6,5. And then you end up with 0,031 moles of C4H10. Now I've worked out the number of moles of that butane, and now I just need to convert to mass. Very important, remember, for that mass down there, don't include that 2. We've already used that. It's just the molar mass of the substance. And then you end up with a mass of 1,78 grams of butane. Now is the time to pause this video and do number 2, 3, and 4, and then just come back to see if you've got it right. In question 2, they ask us what mass of glucose will be produced when 100 grams of carbon dioxide reacts completely. Now, don't be alarmed if you don't know the formula for glucose. If you look at this, I'm sure you know carbon dioxide, and you know water, and you know oxygen, so that must be my glucose. They're asking what mass glucose. So for glucose, we're looking for the mass, and they give us the mass of the carbon dioxide. And then I'll start with what they give you, work out the moles of that, then do the stoichiometry with the ratio, and then if I've got the moles of glucose, then it's just quickly conversion to mass. So here you had to work out the moles of CO2 first. Then we had to go from the CO2 to the glucose, and in the equation they tell you the ratio is 6 to 1. So you had 6 to 1, and then I used the 2,27 moles that I arrived at over there, and then you end up with 0,37 moles, and that is now my moles of glucose. So now I have to convert to mass. So I'm working with N equals M over big M, and I need the molar mass for that glucose. And there, if you worked it out, I end up with 180 grams per mole from my periodic table, and then using it, you should have ended up with glucose being 68,04 grams. In number 3, they asked you to calculate the volume of the nitrogen gas at standard temperature and pressure that will be produced when 1,5 times 10 to the 24 N2O5 molecules decompose. So let's look at what they give you and what they ask. They're asking us for the volume of the nitrogen dioxide, and they're giving us a number of particles there for the N2O5. So now I'll need to convert what they give me to moles, then work with the ratio 2 to 4 to get the number of moles of NO2, and then just convert that to volume. So quickly in step 1, we're using that in our equation to get the number of moles of N2O5. Next up, you had to take the N2O5 to NO2, so we started with a ratio 2 to 4 according to the equation, substituted, and cross multiplication, or just times 2, gave you 4,98. And then we had to work out the volume. And since we are at standard temperature and pressure, I could use the 22.4, and I ended up with 111,63 cube decimeters, or something around there. You might have a little bit rounding difference depending on what you do. Remember, try to keep all the numbers in your calculator so that you actually work with more places after the comma. But they will take it right if you've always rounded to 2, or if you've never rounded until the very last step. Just remember, in that very last step, you need at least 2 numbers after the comma. In number 4, they asked you to calculate the volume of a solution, right? So that's a hydrochloric solution, and they're asking you the volume that is needed to produce 3,36 cube decimeters. That is a volume, and this time it's a gas. So don't get confused. Volume of solution, volume of gas. So what do we have here? For that solution, we've got the concentration that they're asking us the volume. I need to end up here, and they give us the volume of the chlorine gas. So first I'm going to take the volume that they give me, convert to moles of Cl2, then from Cl2 to HCl, that is going to be stoichiometry with the ratio 16:5, and then get the volume. So the first step was just to convert that volume to moles. Then you had to go from that one to that one. What do we know? HCl to Cl2 is in the ratio 16:5, and I am looking for the HCl. I have the chlorine, 0.15 that I worked out down there. And then it's just cross multiplication to make the maths easy, and I end up with 0.48, and now I've got the moles of HCl. And now I'm going to convert that to volume, and remember now we're not working with a gas, so I'm not going to use the gas equation. I'm working with a solution. This is easy to end up with the volume of that solution that is needed. Right guys, that's all in this video. I hope stoichiometry is not something new for you anymore.